So harmonic percussive source separation. I'm going to play it, and then we're going to go and talk about how it works. Here's this drum loop that we are probably sick of at this point. And here's the algorithm working. So here's just the harmonic part, according to this algorithm. And here's just the percussive part. So the way that this algorithm works is it takes a spectrogram. Okay. And it looks for what we could call ridges in this spectrogram, both vertically and horizontally. We're looking for some ridge where there's, if we imagine this heat map is a third dimension coming out of the screen. Some ridge where there's a line of high values. This could be like an onset like this, or it could also be a partial, like sustaining through time, right? And this we're going to assume is going to be the percussive part, and this we're going to assume is going to be the harmonic part. So that's what we're separating. The way it does that is it takes a spectrogram, and in both directions, it applies what's called a median filter across one part of that. So here is a single FFT bin through time. So we're looking at just one band of frequencies, right? One FFT bin through time. Here are 6 onsets. Okay. Applying this median filter looks at a kernel going across all of these values, across time in this case, and looks at like 11 or 13 or 7, some number of adjacent values, and then takes the median value and applies that as being the new value at this spot. And so we can imagine what that would do is it would remove these massive outliers, right? If we're always taking the median value. And so the blue line is the original FFT bin information. The orange line is the smoothed out version after the median filter is applied. And if we imagine doing this on every FFT bin in a spectrogram, what we'll end up with is something where these are these across time like this. So all of those peaks that used to be there are now much lower. They've essentially been removed. And so we end up with what is called the harmonic enhanced spectrum, where we sort of lose those attacks by the median filter, and we still have this harmonic information. Then we do the same thing in the other direction. So here's a single FFT frame, right? And these are all the bins. So we have the frequency here and the loudness here. And we apply the same median filter operation to all of the FFT frames in a spectrogram. And of course, what this will do is sort of dampen all of those spectral peaks, those partials or spectral peaks that are present in that FFT bin. And we'll end up with what we call the percussive enhanced spectrum, where all of that partial information has sort of been dampened, and we end up with these sharp ridges that are strengthened or enhanced the percussive elements. Next, what we do is we compare our harmonic enhanced spectrogram against our percussive enhanced spectrogram, and we create a mask, a harmonic mask and a percussive mask. And the binary part I'll explain in a moment. Essentially what we do is at every point in this spectrogram, we just compare the value here and the value here, and whichever one is higher, we say, if it's higher in the percussive part, that must be part of the percussive sound, the percussive source. And so in the percussive binary mask, we'll put a 1. And in the harmonic binary mask, we'll put a 0. And you'll see other parts where the harmonic element is higher than in the percussive enhanced spectrum. And so for that spot, we'll have a 1 in the harmonic binary mask and a 0 in the percussive binary mask. And binary here is referring to the fact that these masks will always have values that are just 0 or 1. It's just a binary decision. The mask will either just be a 0 or a 1. So once we have these masks created, we then take the original spectrogram, multiply it with the binary mask and the percussive mask, meaning for every position in the spectrogram, we just multiply the value by either a 0 or 1. So we'll get either nothing there or the original magnitude, whatever it was, will be there. And that becomes the spectrogram for our harmonic component output. And then what we can do is use the original phases to do an IFFT with the original magnitudes that are masked, and then turn that back into an audio signal. This is when we're using a binary mask. And again, it's just we compare, and if it's higher, we get a 1 in the mask, and if it's lower, we get a 0 in the mask. That's the binary masking. There's also the option, and in fact, what we were just hearing, is using what's called a soft mask, where we don't say 0 or 1. These are the masks here. We don't say 0 or 1. We allocate the relative amount to each position in the masks. So if here the value is like, 0.2, and here the value is 0.9, the total would be 1.1. So we'd have 0.2 divided by 1.1 would give us the, apportioned amount of energy according to these two spectrograms here, and 0.9 divided by 1.1 would give us the apportioned amount of energy for this spot here in the percussive enhanced spectrogram. So that what we get now is if we were to add these two masks together, they would exactly sum to 1 at every point in our summed spectrograms. Then when we multiplied the masks by the original spectrogram, because we've appropriately apportioned them, we know that we're allocating all of the energy from the original into either the harmonic output or the percussive output, but done in a way that's called a soft mask. It's sort of more relative approach rather than a strict binary approach. So here is just the harmonic part with the soft masks. Here's just the harmonic part with the binary masks. So you can hear there's some more like spectral artifact in there. And so that's part of the reason why people often prefer soft masks. If you're just going for the percussive part, the binary mask really tightens up that percussion part pretty extreme. Again, there's a harmonic sort of spectral artifacts in here, but it can make that that percussive part a lot tighter, a lot kind of something. If we turn it back to the soft mask, there's a little bit more ring happening there because of the soft masking, but the binary mask is much tighter given the artifacts. So that's a trade-off. There's a third option actually, which is using soft masks, but in a slightly different way. And there's a residual that is computed. If we do that and then listen to the residual, can you even hear that? It's just a little bit of like FFT juice just kind of dancing around. With the HPSS, I haven't found that the residual is very useful or interesting. I haven't really found a need to be thinking about or using this third option. The soft mask and binary mask is a more salient choice. In HPSS, there are a few parameters. There's the harmonic filter size and the percussive filter size. And this is the size of the median filter that is applied. A bigger filter will cause more smoothing. A smaller filter will cause less smoothing in the median filter smoothing process that we saw. The harmonic filter is a measure in spectral frames because that's what we're smoothing across, right? And so as that increases, it will increase the latency for the reason we have seen before. The harmonic filter size by default is 17. So the latency by default is 17 FFT frames, which is not trivial. The percussive filter size is measured in spectral bins because that's the dimension we're filtering across, right? That one doesn't affect latency at all. In the original paper, which you can find on the FluCoMa website, the authors of the paper say that the harmonic filter size and percussive filter size don't have too much an effect on the sound, on the results, which I've sort of found to be true. I've tried to play around with those parameters, see if I can build intuition about adjusting them and how the results are affected. You can get different results, but it's sort of like, oh, that's different. Is that better or worse? The default settings that they've indicated in the paper that we've replicated in the object are sort of like, they're good settings. They're the settings that I use. What they do say is that the FFT settings can have a pretty strong impact on the sonic results, which I have found to be true. Shortening up the FFT window and shortening up the hop size can make the percussive part a lot more snappy, as one would imagine. Sort of our time resolution is much smaller. And if you increase these FFT sizes, you'll get spectral smearing, right? So just sort of the common FFT size adjustments. If you're looking for a change to the sonic results, adjusting the FFT size and hop size is going to give you more varieties that might be more useful more quickly than playing with the harmonic filter size and percussive filter size. Separating the harmonic from the percussive and then processing them separately. A little example. This is the original, unprocessed. Little synthesizer scratch. It's obviously a pretty good candidate for this because the harmonic and percussive are very different sort of sound objects in this, but once they're separated,